Hello, good afternoon, all. I am Saurabh, and I welcome you to this session for the NPTEL course in Applied Thermodynamics. In today's session, we will discuss refrigeration and air conditioning systems. We will try to solve some problems, which I hope will be helpful for you in clarifying any doubts if you have any, and it will be helpful for solving your assignment problems. Okay, so we will begin with question number 1. So question number 1 says the trade name for ammonia as refrigerant is. So you know that ammonia is used as refrigerant in many refrigeration systems, and refrigerants have their some special names. Okay, so like R314, R22. Okay, so like that ammonia also have some name, trade name. So we have to tell what is the trade name of ammonia as refrigerant. Okay. To answer this question, you should know certain rules using which you can name any refrigerant. Okay, so there are some rules which are used to name any refrigerant if you know the chemical formula of that compound. Okay, for example, NH3, you know the chemical formula NH3. So using some rules, you can name this refrigerant by their trade name. Okay, so before answering this question, we will see some of those rules which are very useful for naming some very common refrigerants. Okay, so for example, if you have any single organic refrigerant, okay, so in a single organic refrigerant, you will have some carbon, you can have some hydrogen, some chlorine, some fluorine. Okay, CFC you call them, right? Chlorofluorocarbon. Okay, for naming these refrigerants, organic refrigerants, you have certain set of rules. Similarly, for inorganic refrigerants, you have certain set of rules. Okay, for example, if you have a organic refrigerant, a single organic refrigerant, so there will be few letters. Okay, the first letter will tell you the number of carbon atoms minus 1. Okay, for example, if any refrigerant, in the chemical formula of that refrigerant, if there are 2 carbon atoms, then in the trade name of that refrigerant there will be 2 minus 1. Okay, we will take this example. For example, Cl CH ClF2. Okay, so in this there are 1 carbon atom, right? So, and one more thing, for single organic refrigerant, you have to put 1 R. Okay, so first you will have to put 1 R. So R represents that you are having single organic refrigerant. Okay, so 1 R will be there. Then number of carbon atoms, how many carbon atoms are there? 1 carbon atom. So 1 minus 1, 0. Okay, then for the second letter, you have hydrogen atoms plus 1. So in CHClF2, you have 1 hydrogen atom. So 1 plus 1, 2. Okay. Then you have fluorine atoms, number of fluorine atoms. Here you have 2 fluorine atoms. So 2. Okay. So you have R. If you remove the 0, you have R22. Okay. So this is the trade name for CHClF2. Similarly, you can name CH2F, CF2. Oh, this should be CF3. Okay. So similarly, you can name this compound as well. Okay. So CH2F, CF3. If I make the structure, then it will be something like this. You have to see there. Okay. So F, 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 then H, H, and one F. Okay. So if you want to name this refrigerant, then how many carbon atoms you have? You have 2 carbon atoms. And one more thing, again you will have to put R, right, because it is single organic represent. So for this you will have to put one R. Then number of carbon atoms, how many carbon atoms are there? Two carbon atoms, right? So 2 minus 1, 1. Okay. Then number of hydrogen atoms, how many hydrogen atoms are there? Two hydrogen atoms, right? So 2 plus 1 is equal to 3. Then so it is 3. Then how many fluorine? 1, 2, 3, 4. 4 fluorine. Okay. So 4. So it is R1, 3, 4. Okay. And one more space you can see, there can be some letter, okay, like A. So A basically represents the isomer order, okay, how these atoms are bonded to form this molecule. Okay. So for this particular represent, we can put one A, which basically tells this structure. Okay. So this is how we name the organic representants. Similarly, you have some set of rules for naming inorganic representants. Okay. For naming inorganic representants, first you put 7 in front of the name. Okay. So the first letter is 7. Then 2 letters for the molecular weight. Okay. So for example, if you want to name ammonia, so first you will put 7, right? Then molecular weight. So what is the molecular weight of ammonia? Molecular weight of ammonia. So if you calculate, then 14 for nitrogen and 3 hydrogen, so 17. So 717. Okay. So this is the name for ammonia. And of course, you will have to put one R. Okay. Similarly, if you want to name carbon dioxide, then 7, right? You have to put 7. Then molecular weight of carbon dioxide. Molecular weight of carbon dioxide is 44. So it is 744, right? So this is how you name any, representants. There can be other representants which can be in the form of a solution. Okay. Solution basically mixture of more than one representants. So for those type of representants, you have another set of rules. Okay. So I'm not going through those rules, but you should know that there are certain rules using which you can name any representant. Okay. And for ammonia, the trade name will be R717. Okay. Okay. So I hope now we can answer this question. So for ammonia, it is R7 and then molecular weight of ammonia 17. Okay. So R717, this is the trade name for ammonia. Okay. So I hope this is clear and we can move to the next question. Question number 2. In an ammonia absorption refrigeration system, which one is used as refrigerant? So ammonia absorption refrigeration system. So first of all, absorption refrigeration system. What do you do in absorption refrigeration system? In absorption refrigeration system, you remove the pump, and instead of pump, you put some some complicated system which do exactly the same thing which pump was doing. And why we are doing this? Because to run a pump, you need electricity. Okay. Or any high quality energy, right? So you don't want to waste that high quality energy, or you don't want to waste electricity, then you can, and you want to use low grade energy. That's why you are using absorption refrigeration system, because when you are replacing that pump by some other complicated system, that complicated system basically use heat. Okay. And heat is a low grade energy. Okay. So basically using a low grade energy, you can run your refrigeration system. Okay. So in an absorption refrigeration system, there is one refrigerant, because for any refrigeration system, there will be some, refrigerant. a working fluid, and there will be some absorption system. Okay, so in an ammonia absorption refrigeration system, which one is used as refrigerant? So I will again show you some diagram, then it will be become more clear. In an simple refrigeration system, what you have? You have one condenser, right? Then you have some expansion wall or capillary tube. Then you have evaporator. Then you have a pump, right? Then you have a pump. Okay. Then you have a pump. And to run this pump, you need high grade energy, right? You need a high grade energy. But you don't want to use the high grade energy. You want to use low grade energy. Low grade energy is nothing but the heat. So you replace this pump by this, this complicated system. Okay. And this system, which is enclosed by this dotted rectangle here, that does exactly same thing which pump was doing. Okay, so what pump was doing? Pump was providing you the high pressure ammonia. Okay, here you have pure ammonia that is at low pressure, and here you have ammonia that is at higher pressure. Okay, so this system that is enclosed in this dotted rectangle, that the purpose of this whole system is to provide you the high pressure ammonia. Okay, so this pure ammonia is going in this absorber, and you are getting the solution of ammonia and water. This solution is pumped to this regenerator. Okay, then in this the regenerator you are heating this solution, and this ammonia is coming out, and you are getting high pressure ammonia. Okay, so this is the whole system. So this pure ammonia is the working fluid. This is the main refrigerant. Okay, so this is the refrigerant. So now you can answer this question. In an ammonia absorption system, which one used as a refrigerant? Ammonia is used as refrigerant, right? If it is clear, then we can move to the next question. Okay. So again, I will repeat the purpose of this whole system. You can highlight this system. The main purpose of this system highlighted is to provide the refrigerant at higher pressure. Okay, just to pressurize this thing. Okay, in your vapor compression system, what you have? You have a pump, not pump, I should say a compressor. Okay, so I'm sorry, I will write here compressor. Okay. And the purpose of compressor is to compress or to pressurize the working fluid, the refrigerant. Okay, and you know that compressors consumes a lot of energy, right? This condenser is nothing but just coil. This evaporator also just coil. This expansion valve is just one small very thin tube, the capillary tube. Only the compressor is the power consuming device. Okay, and this runs on high grade energy, basically electricity, and you don't want to use that electricity. You don't want to use high grade energy, so you are replacing that compressor by this complicated system. And here you can see you are using a pump, and pump that uses significantly lower energy as compared to compressor, right? Compressors are used for compressing a gas, to pressurize a gas, and pumps they work for liquids, and the change in specific volume of liquids is very small. That is very negligible. So the pump work is usually very smaller as compared to the compressor work. Okay, so in this by this this whole system, you are basically replacing the compressor. So you are you will not have to provide that much energy. Okay, so I hope this is clear. Okay, and we can move ahead to the next question. Question number 3. It says, in a vapor compression refrigeration system, the heat rejected by the refrigerant condenser is 175 kilojoule per kg. Okay. And the heat absorbed by the refrigerant in evaporator is 125 kilojoule per kg. COP, the coefficient of performance of the refrigeration system is. Okay. So we have to find the COP. And COP, coefficient of performance, you know, what is COP? Coefficient of performance. What is coefficient of performance? Coefficient performance is how much heat you are removing, right? In case of refrigeration, the purpose of refrigeration is to remove the heat from a cold environment and to throw that heat into a hot environment. Okay, so in case of a refrigeration, the purpose, your target is to remove the heat. Okay, so how much purpose is being solved? Okay, how much heat is being removed, that is your desired output. Okay, so how much heat you are removing, q out, divided by how much work you are uh, providing. Okay, so this heat is removed basically by evaporator, right? So this is by evaporator and this by compressor. This work is provided to the compressor. Okay, and for heat pump, the purpose of heat pump is not to remove the heat, it is to dump the heat. Okay, so there your purpose is not to remove the heat, it is not the q out, this is q out plus this work instead of q out, better if you can write q in. Okay, why I am saying this? Because this is, let us say, at here, from here you are removing some heat, q out. Okay, this is your cold environment and you are putting some work input. Okay, you removed heat removed, and here q out. So it is better to write it clearly, heat removed from the cold region. Okay, and you are throwing this heat to the hot region. Okay, so heat rejected by the refrigerant condenser is 175. Okay, so this thing is 175 kilojoule per kg, and heat absorbed by the refrigerant in evaporator is 125 kilojoule per kg. Okay, so this 175 should be the summation of Wn plus Q removed, right? Heat removed. Okay, so work input you can find as 175 minus 125 kilojoule per kg, right? So basically you're providing 50 kilojoule per kg. This is your work input. Now you can find the COP. COP will be how much heat you are removing, 125 kilojoule per kg divided by work input, that is 50 kilojoule per kg. So you will get how much? 2.5, right? So this is the correct option, right? If it was a heat pump, then your interest was not how much heat you are removing, but how much heat you are getting, right? Then in case of heat pump, COP of heat pump, then it would have been 175 divided by 15, right? But here it is refrigerant. Okay. So COP of a heat pump is 1 plus COP of a refrigerator. Okay. But anyway, here it is refrigerator, so the COP should be 2.5. Okay. I hope it is clear, and we can move to the next question. Question number 4 says, in an ammonia water vapor absorption refrigeration system, the amount of ammonia that can be dissolved in water is inversely proportional to the temperature. Okay. So again, we will visit this diagram from previous question. Here you can see we have one absorber, right? What we have? We have a absorber. And what absorber is doing? An absorber, basically ammonia is being dissolved in the water. Okay. So you are getting ammonia water solution. This process of dissolving of ammonia into this water, this is a exothermic reaction. Okay. When ammonia get dissolves in water, the heat is released. Okay. So this is an exothermic reaction. So if you want to dissolve more and more ammonia into the water, then you will have to take out that heat that is being generated during this dissolving process, right? You might have studied in equilibrium that uh, if you want to increase the rate of forward reaction in case of an exothermic reaction, you should take out the heat, right? Ammonia dissolves in water, and this process is exothermic, right? Heat is released, right? So if you want to dissolve more ammonia, take out the heat released during exothermic process of dissolving. Okay. In the question, what it is asking, it is saying that it is inversely proportional to the temperature. So it is correct, right? If you remove the heat, so basically you are reducing the temperature, and you are getting being able to put more and more ammonia, right? To dissolve more ammonia, you need to reduce the temperature. Okay. So reducing the temperature basically means taking out the heat, right? So how much ammonia can be dissolved, that is inversely proportional to the temperature. So this statement is and true. This is a true statement, right? So option A, true, right? I hope this is clear, and we will move to the next question, question number 5. Question number 5 is saying, in an actual vapor compression system, the refrigerant temperature in the evaporator is higher than the cold region temperature. We have to tell whether this statement is true or false. So this is very, easy question. By common sense, you can answer this question. The purpose of a refrigerator is to take out the heat from the colder environment, right? And how that heat is taken out from the colder environment? By sending something even more cool, right? And that even more cool thing is nothing but your cooled refrigerant, right? When the refrigerant comes out from the capillary tube or the expansion wall, that is very very cool. Okay, and the temperature of that refrigerant is smaller, is lower as compared to your cold environment from where you want to remove the heat. So because of that temperature difference, heat is transferred from the cold environment to the refrigerant, okay, in the evaporator, correct? So to remove the heat from the colder environment, the temperature of the refrigerant should be even smaller, right? So it should be smaller than the temperature of your cold environment, okay? But here it is saying that the refrigerant temperature in the evaporator is higher than the cold region temperature. So this is of course not correct, right? If the temperature of the refrigerant is higher, then the heat transfer will be from the refrigerant to the cold environment, right? So that is just opposite of what we want. We want to take out heat from the cold environment, but if the temperature of refrigerant is higher, then instead of taking out high heat, we are adding the heat, right? So this is not correct. So this is the false statement. What will be the true statement? True statement will be like just opposite of this. In an actual vapor compression system, the refrigerant temperature in the evaporator should be lower than the cold region temperature. Okay. So I hope this is clear. Now we will move to the next question. Question number 6. It says, in the expansion process of refrigerant in the throttle valve, okay, so throttle valve is used for expansion process. Sometimes capillary tube is used for expansion process. So throttle valve of a vapor compression system, which of the following thermodynamic parameter does not change? We have four options. One is density, specific volume, specific enthalpy, or the temperature. So again, you can answer this question by just your basic knowledge, common sense. So it is saying expansion process. So during expansion process, density should reduce, right? Because you have certain amount of matter and you expand that matter, then what will happen? Density will decrease, right? So density will reduce. So it is not constant, it is changing. Specific volume, specific volume will increase, right? If you have, let us say, 1 kilogram of something and you are expanding that, then specific volume will increase, right? That is the meaning of expansion. So again, the volume is also increasing, that is also not constant. So it is changing. Temperature, what about temperature? In case of refrigeration system, temperature is dropped during this expansion process. Okay. There is something called Joule-Thomson coefficient. So I encourage you to read some concept related to Joule-Thomson coefficient. There are some curves, some inversion curves. Okay, when the temperature is reduced, when the temperature is not reduced. So if you read that, then it will become more clear. But anyways, by common sense, you know that in the thermodynamic, in the refrigeration systems, you want to reduce the temperature. You want to cool down your refrigerant, and that cooling process, that reduction of temperature occurs during the expansion process. Okay, so the temperature during the expansion process, that decreases. Okay, that is also not constant. So density during the expansion process, it decreases. Volume, specific volume during the expansion process, it increases. Temperature during the expansion process, it again drops. Okay, so density drops, specific volume increases, and temperature also decreases. It's the specific enthalpy that is almost constant. Okay, almost constant. Okay, so which thermodynamic parameter does not change? So the correct option should be specific enthalpy. Okay, so the expansion in a throttle valve, that is isenthalpic, right? Okay, so this is very important point to keep in mind. It is useful many times when you solve numerical questions, because sometimes you need enthalpy at 2 points. So if you know the enthalpy before the expansion, then you can use the same value of enthalpy after the expansion, because the expansion process can be treated as almost isenthalpic. Okay, so I hope this is you got the point. Now we will move to the question number 7. Question number 7 says a vapor refrigerating system operates on a reversed Carnot cycle. So Carnot cycle you have studied in vapor power cycle, in the power cycles. Okay, so this is an ideal or imaginary cycle that gives you maximum efficiency, and the reversed Carnot cycle is the imaginary cycle for refrigeration that gives you the maximum coefficient of performance. Okay, the temperature in the condenser coil is 27 degree, and that in evaporator coil is 23 degrees Celsius. For a work input of 1 kilowatt, how much heat is pumped from low temperature reservoir? Okay, so you have a low temperature reservoir. Some heat is pumped out. Okay, and you are giving some work input, heat removed, and heat is thrown into a high temperature reservoir, right? Heat input, let us say. Okay, so you have studied this relation. You removed, or let us say write it here QL, because this is the heat exchange corresponding to low temperature, and it is heat exchange corresponding to high temperature. You have studied this relation. QL by QH is equal to TL by TH. Correct? Here TL is how much? Minus 23 degrees Celsius, or 273 minus 23 Kelvin. So it is 250 Kelvin TL. And how much TH? TH is 273 plus 27 Kelvin. So it is 300 Kelvin. Correct? And this QH, this will be QL plus work input, right? From the first law. Okay. So QL, and instead of QH, you can write QL plus work input is equal to 250 Kelvin divided by 300 Kelvin. Okay. So you can write this as 3QL is equal to 2.5 QL plus 2.5 WN. Okay, so for Wn is equal to 1 kilowatt, you have 0.5 QL is equal to 1 kilowatt. Sorry, 2.5 kilowatt. So from here you get QL is equal to 2.5 kilowatt divided by 0.5. So you get QL is equal to 5 kilowatt. Okay. So in a reversed Carnot cycle, which is working in the temperature limit of 27 degree and minus 23 degree Celsius, for a work input of 1 kilowatt, you will be able to remove 5 kilowatt of heat from the low temperature reservoir. And what will be the COP of this refrigeration system? COP will be QL divided by WN. COP will be 5, right? But in a real refrigeration system, that cannot work on a Carnot cycle. Okay, so you will not get the COP of 5. Okay, anyways, uh, the answer for this question is 5 kilowatt. Okay. I hope this is clear and we can move ahead. Question number 8. Question number 8 says the condensation process of refrigerant in a vapor compression cycle is carried out at constant. So that is at constant volume or constant pressure or constant enthalpy or constant temperature. So this question is also you can answer. We will make a TS diagram. Very easy. Okay. So here is the condenser. This is the condenser. Process 3 to 4. This is condensation. And this process 3 to 4, this is at constant pressure. Okay, so here is our isobaric line. This is basically constant pressure line. Okay, the condensation process in a vapor compression cycle is carried out at constant pressure. Okay, this was an easy question and I hope this is clear. If there is no doubt, then we will move to the question number 9. Question number 9 says, which of the following cooling device does not use low grade energy? One is vapor compression heat pump, ammonia water vapor absorption system, lithium bromide water vapor absorption system, or all of the above. So you will see all these options one by one. The vapor compression heat pump we have already discussed, right? So what is there in a vapor compression system? There is one evaporator, right? Then there is some expansion valve, then there is a condenser, right? Sorry, I will write it again. Okay, so there is one expansion valve. So after expansion valve, you get very cool refrigerant. Then you have evaporator, where heat is removed from colder environment. Then you have a compressor, and then you have a condenser. Okay, and these are two absorption systems. So absorption system also have the same components, except condenser. Okay, so there is no sorry, except compressor. So in absorption systems there is no compressor. Okay, and compressors, they use high grade energy. So in absorption systems, compressor is replaced by a special arrangement, and the purpose of that special arrangement is to provide high pressure refrigerant. And this special system, this special arrangement, this uses heat, and heat, is a low grade energy. Okay, so vapor compression system, vapor compression heat pump has a compressor, and that use high grade energy. And absorption systems does not have compressors, and that's why they use low grade energy. So now you can answer this question: which of the following cooling device does not use a low grade energy? Vapor compression system, vapor compression heat pump, because it has a compressor, and to run the compressor you need high grade energy. You cannot run the compressor by using low grade energy directly. Okay, so option A should be the correct option. Okay, so I hope it was clear. Now we will move to the question number 10. Question number 10 says lithium bromide, being a salt, has a strong affinity for water vapor because it has very low vapor pressure. So lithium bromide system, that is a absorption repression system, right? Lithium bromide, water vapor absorption refrigeration system. So it is very similar to ammonia system, okay, that we have seen here, ammonia absorption refrigeration system. But only this, instead of pure ammonia, we are using water vapor, and here for absorption system you are using lithium bromide. Okay, so the lithium bromide is used to absorb the water vapor, and the water vapor is used as refrigerant. Okay, in ammonia system, ammonia is used as refrigerant and water is used for absorption. Okay, and in lithium bromide system, water vapor is used as refrigerant and lithium bromide is used for absorption. Okay, so here lithium bromide, this is absorbent, and water, this is your refrigerant. Okay, and water vapor can be easily absorbed in the lithium bromide because it has very strong affinity for the water vapor. And so this statement is true. Okay, this is a true statement. I hope you have no doubt, and we can move to the next question. For an question number 11, so it says for an ideal vapor compression cycle, which is consisting of a compressor, condenser, throttling valve, and evaporator, which of the following components undergoes a reversible process? Okay, so there are four components: compressor, condenser, throttling valve, and evaporator. So 1 to 2 is our evaporator. 2 to 3 is compressor. 3 to 4 is condenser, and 4 to 1 throttling valve. Okay, in an ideal vapor compression system, all the processes are reversible except the throttling process, because throttling process is always, irreversible. Okay, evaporator evaporation. This process can be reversible in ideal case. In ideal case, this process is also reversible. This process is also reversible, but throttling processes are always irreversible. And in real case, process 2 to 3, this can also be irreversible. Okay, but in an ideal case, the compression process is also reversible. Only throttling process is irreversible, and throttling is always irreversible. Okay, so you can see the entropy changing. Okay, so if it was an reversible process, you will get a vertical line, but here you can say from 4 to 1, you are moving towards right hand side. Okay, so entropy is basically being generated, so that is the indication of being uh, of an irreversible process. Okay, so now you can answer the question. The correct option should be option C, throttling valve, because in the throttling valve you are having throttling process, and that is irreversible, so this does not undergo reversible process. But what we have to tell in an ideal vapor compression cycle, the consisting of this, which of the undergoes reversible process. Okay, so we have to tell how, which of these goes which undergoes reversible process. So compressor, condenser, and evaporator. Okay, and throttler, the throttle bar, it undergoes a reversible process. So option A, B, and D. Three options are the correct option. Okay. I hope this was clear, and we can move to the next question. Okay. Question 12 says a refrigerator uses refrigerant R134A as working fluid. Okay. And operates on an ideal vapor compression refrigeration cycle between 0.14 and 0.8 megapascal. Okay. If the mass flow rate of refrigerant is 0.05 kilogram per second, we have to find the rate of heat removal from the refrigerated space, the power input to the compressor, and the rate of heat rejection to the environment. And we have to find the coefficient of performance of the refrigerator. Okay, so we will begin by making TS diagram. So the ideal vapor compression refrigeration cycle. This is the TS diagram. Okay, the pressure range is given. Okay, so P2 is equal to P3. This is isobaric process and pressure is 0.8 megapascal. Okay, and P4 is equal to P1, and that is equal to 0.14 megapascal. Okay. What else is given? Mass flow rate of refrigerant is given. This is given to be 0.05 kilogram per second. Okay, and we need to find the other thermodynamic properties at remaining points. And refrigerant used here is R134A. So we'll have to use the property table for this refrigerant. So unfortunately, the properties are not given. So I will check if I can get the tables. Okay, here's the table. We'll have to use the table for R134. So here it is. Okay, here it is. A11 to A13 or A14. A11. Okay, here it is. This is temperature wise, and this is pressure wise. We have to check at 8 megapascal. That is basically 80 kilopascal, correct? So at 80 kilopascal, what is the enthalpy of saturated gas? Or we can begin with this point 1. Sorry, this is 800 kilopascal. And this is 140. So we have to check here 140 kilopascal. We have to check the enthalpy of saturated vapor, Hg. Here it is 239.19. Okay, so H1, which is basically the enthalpy of saturated gas at this corresponding pressure of 0.14 megapascal, and it is given to be 239.19 kilojoule per kg. And entropy at this point is this 0.9447 kilojoule per kg Kelvin. Okay, so we have the values at point 1. Now let us come to point 2. At point 2, this is, is in the superheated region. Okay, so at point 2, you have pressure and you have entropy, because this is an isentropic process for ideal vapor compression system. So S1 we have already found out. So you can use this table, and pressure is how much? 800 kilopascal. So you'll have to use superheated table. So this is superheated table. You can also use the charts. At superheated table, you will have to use this value 0.8 megapascal, and entropy is 0.944. So it's this values will be somewhere here. Okay, so you can use some interpolation and you will get the other values. You'll get the temperature value. What I have here, that I will use here. So I will use here H2. So how will be the H2? It will be around 276 to 286. Okay, so it will be something in between. Okay, here I am using 275. Okay, you can use some interpolation, some sort of averaging. Okay, So you have H2 at 0.2. Now coming to point 3. This point 3 is, is the super, saturated liquid. Okay. Again, the pressure is 800 kilopascal or 0.8 megapascal. But you'll have to use saturated liquid table. The pressure is 800 kilopascal, this table. We have to find the enthalpy of saturated liquid. This is 95.48. Okay. S3 is 95.48 kilojoule per kg. Okay. And from 3 to 4, this expansion process can be considered to be asymptotic. So H4 will be nearly equal to H3. So this can also be taken as 95.48 kilojoule per kg. Okay. So now we have all the values. Now we can proceed. Okay. So the first part, what it is asking. It is asking for rate of heat removal. Right. So what will be the rate of heat removal? Where's the heat removal? Heat removal is from 4 to 1 in the evaporator, right? So rate of heat removal will be equal to m dot h1 minus h4. Okay. M dot is given in the question. This is 0.05. H4, sorry, H1, we have found out from the table, it is 239.19 minus H4 is 49.48 kilojoule per kg. Okay. This is 19. So it is 7.185 kilojoule per second, right? That this is rate of heat removal. Okay. And the power input to the compressor. What will be the power input? Power input, where you are providing the power? In the compressor. And compressor, the compression process is from 1 to 2. So m into h2 minus h1. So m again is 0.05, sorry, kilojoule per kilogram per second, and h2 is 275.4 minus h1 is 239.19. kilojoule per kg. Okay. So work input is 1.181 kilojoule per second. Okay. So this was asked in part A. What else is asked? Asking rate of heat rejection to the environment. So here the heat rejection is taking place. Heat rejection is taking place here, right? From 2 to 3 in the condenser. Okay. So this will be equal to m into m2 minus, sorry, h2 minus h3. Correct? And if you substitute the values, then you will get the values. And one more thing, you know, that heat rejection, this is also equal to the heat removed plus work input. So from there also you can find the same value. Okay. And you can check by yourself then that these value will be same. Okay. So 7.185 plus this is heat removal rate plus work input rate. So 7.185 plus 1.81, so 8.995 kilowatt. And similarly, if you try to calculate it from here, 0.05 H2, how much is H2? 275.4, 275.4 minus H3, how much is H3? 95.48. Then these values will be same. Okay. 7.185 minus 1.81. Sorry. To 75.4 minus 95.48. So this is again 8.996 kilowatt. Okay, so they are basically same values, right? Okay. What else? COP of the refrigerator. So COP is how much heat is removed from the cold environment divided by how much is the work input. Okay, so how much heat is removed? 7.185. And how much work input? 1.81. This is 3.96. .97. Okay, so this is COP. Okay, so you have calculated all the values, whatever was asked there. Okay, so this is COP. This is rate of heat rejection to the environment. This is rate of work input to the compressor. This is rate of heat removal from the cold environment. Okay. And this was your vapor compression system. So 3 to 4 is basically a expansion in the throttling valve or some capillary tube. For expansion, you can also use turbine. There are various reasons you are not using turbine. But if you imagine that you are using a turbine, then you will be getting some work output in the process 3 to 4, right? And some part of that work can be used to run this compressor, right? So the net, the total, the overall work that is required from our side to the compressor, that will be reduced. So in that case, COP, we can expect that COP should be increased. Okay, so how much change will be there? I encourage you to try it by yourself. Okay, so just calculate the work output that you will get from process 3 to 4 and subtract that work output from the work that is you are providing from 1 to 2. Okay, then you calculate COP again, then you will find you will get increased COP. Okay, so you can expect some COP around 5 to 5.5, something like that. Okay, so just try to do it by yourself and see the difference. Okay, but we do not use the turbine because it will make system more complicated, right? And there are some other problems involved. For example, turbines usually can handle single phase. Okay, because if there are multi-phase, then blades can be corroded, but the capillary tubes can be they can handle easily the mixture. Okay, the throttling valves can uh, handle the two phase. Okay, so as shown in this diagram, you can see this process 3 to 4. This is in the saturation dome. So this is basically a mixture of liquid and vapor. Okay, so that's why you are using this throttling valve. Anyways, so this is what was asked and we have found all these values. If there is no doubt, then you should move to question number 13. Next question. Question number 13 says refrigerant R134A, again the same refrigerant, I think. Yes. Enters the compressor of a refrigerator as superheated vapor at 0.14 MPa and 10 degrees Celsius at the rate of 0.5 kilogram per second. It was same values, right? So leaves at 0.8 MPa, again the same value at and 15 degrees Celsius. The refrigerant is cooled in the condenser to 26 degrees Celsius and 0.72 megapascal and throttled to 0.15 MPa. Okay. Disregarding any heat transfer and process pressure drop in the connecting lines between the components, we have to find the rate of heat removal from the refrigerated space and the power input to the compressor and the isentropic efficiency of compressor and the coefficient of performance of the refrigerator. Okay, so in the previous question, we were having an ideal vapor compression refrigerator, but here it is not the ideal case. Okay, but again, we can use the property table for R134A and we can solve the question. Okay. Again, we'll have to make this TS diagram. In the previous question, this compression process was isentropic, but here it is, not isentropic. Okay, previously it was isentropic, but here it is, in the ideal case, it is not isentropic. It is some irreversibility is there. Okay, and also it can be outside the dome region, right? So we'll make it little outside the dome. Anyways, process 1 to 2, this compression process, then we have process in the condenser, the isothermal process. Then we have this throttling process, 3 to 4. Okay, this is our TS diagram. Okay, so again we will have to find the values whatever is not given. So P1 is given, right? It is given 0.14 ampere, and T1 is also given how much? 10 degrees Celsius. So from these values we can find the enthalpy, right, from the superheated tables. Sorry, this is the superheated table at 0.14 ampere and 10 degrees Celsius, correct? Sorry, it is minus 10. This is minus 10. Minus 10, this value. So enthalpy at this point is how much? 246.37 kilojoule per kg. Okay. Now coming to point 2. At point 2, you have pressure is equal to how much? 0.8 ampere, correct? 0.8 ampere and temperature is 50 degrees Celsius. 0.8 ampere and temperature is 50 degrees Celsius. Okay. Again, you will have to use the superheated table for 0.8 ampere and 50 degrees Celsius. This, what is the enthalpy here? Enthalpy here is 286. So H3 is 286.71 kilojoule per kg. Okay. Now coming to point 3, sorry, this was point 2, H2. P3 will be equal to P2, and you can use what is the temperature at point 3. Temperature is cooled in the condenser to 26 degrees Celsius. Okay, so at the exit of condenser we have T3 is equal to 26 degrees Celsius, and that is in the subcooled region. We don't have the subcooled table, so what we can do, we can just assume that enthalpy at point 3 is equal to the enthalpy of saturated liquid at this pressure P3. Okay, so we'll use the saturated table for this pressure 0.8 MPa. Or we can use this temperature, that will be even better, 26 degrees Celsius. That is very near to the saturation line, right? So this value, enthalpy at this value is how much? 87.83, correct? So enthalpy here is approximately 87.83 kilojoule per kg. Okay, sorry. And 3 to 4, the expansion process, that is uh, nearly asymptotic, so H4 will also be approximately equal to H3, so 87.83 kilojoule per kg. Okay, so now we have all these values and we can solve the question. So the first question, first part, what is asked? Asking the rate of heat removal and the power input. So rate of heat removal will be equal to m dot h1 minus h4, right? 0.05 kg per second, and h1 is how much? 246.37 minus h4 is 87.83 kilojoule per kg. So you are getting 7.927 kilojoule per second. What else? Power input. Power input will be equal to from process 1 to 2, right? What is H2? H2 is 286.71 minus H1. How much is H1? 246.37. Two point zero 0.7 kilowatt. Okay. Part B, it is asking isentropic efficiency of the compressor. So what is isentropic efficiency of compressor? That is reversible work divided by irreversible work input. Correct? And what will be the reversible work input? It will be H2 if the process from 1 to 2 was reversible isentropic minus H1 divided by the actual value of enthalpy at point 2. Now again this H2S you can find from the table using the concept that S2 is equal to S1 for the isentropic case. Okay, so if you find this value, it will come out to be from the table. I am writing it 284.2 kilojoule per second. Okay, from the table you can use some interpolation and you can get some approximate value. Okay, so if we just substitute the values, we will get it 284.2 minus 246.37 divided by actual H2 is 286.71 minus 246.37. Okay. 284.2 minus 246.37 minus 286.71 minus 246.37. So we are getting approximately 0.9378. So the isentropic efficiency is around 93.78%. Okay. What else we have to find? The coefficient of performance. What will be the COP? COP will be how much heat is being removed divided by work input. What is the rate of heat removal? This is 7.927. 7.927 kilowatt divided by rate of work input or the power input. This is 2.017. 2.017 kilowatt. So it is around, sorry, 3.93. Okay. So yes, this is what was asked in the question. In the previous question, COP was 3.97. Here it is 3.93. So it is reduced a little bit because of the irreversibilities involved. Okay, so we have found, we were asked to find rate of heat removal, that we have found. We were asked to find the rate of power input, that also we found. Isentropic efficiency was asked, that also we calculated, and the COP. Okay, I hope this is clear, and we can move to the next question. Question number 14. Question number 14 says a refrigeration machine is required to produce ice at 0 degrees Celsius from water at 20 degrees Celsius. Okay, so water is initially at 20 degrees Celsius, and you need to, the machine is required to produce ice at 0 degrees Celsius. Okay, the machine has a condenser temperature of 298 Kelvin. Okay, 298 Kelvin, and the evaporator temperature is 268 Kelvin. Fine. The relative efficiency of machine is 50%. And 6 kilogram of Freon 12 refrigerant is circulated through the system per minute. Okay. The refrigerant enters the compressor with dryness factor of 0.6. The specific heat of water is 4.187 kilojoule per kilogram Kelvin, and the latent heat of ice is 335 kilojoule per kg. Calculate the amount of ice produced on 24 hours. In 24 hours. The table of properties of Freon 12 is given. Okay, so we don't need to use any extra property table because the values is given in this table. So again, we will begin by making this table, TS diagram. Okay, so temperature at point 2 is given. Point temperature at point 3. Where is the temperature given? Okay, condenser temperature. Okay, so 298. So this is also given. 98 Kelvin to 68 Kelvin. Fine. We need to find the other values. So this is HF, this is HFG, and this is SF. Okay. Some values are given, some values we need to calculate. So we'll calculate the missing values and then we'll proceed. For example, H3, enthalpy at point 3 we will need. Okay, So this will be calculated from the table. So the as enthalpy at point 3 will be equal to this point 3 okay. So what is given? We'll just note it down. Mass flow rate of refrigerator is this 6 kilogram of freon. Okay, so mass flow rate is given 6 kg per minute. Relative efficiency is given 3%. Dryness factor as 0.2 is given 50%. No, sorry. 0.6. Okay. So this 0.2 is inside this dome. Okay, because dryness factor is less than 1. Okay, so we'll make the diagram again. Should be something like this. Okay. So HF2 is given 31.4 kilojoule per kg. HFG at 0.2, this is also given 154.0 kilojoule per kg. And HF3, this is also given 59.7 kilojoule per kg. HFG3, this is also given 138.0 kilojoule per kg. Okay. And since process 4 to 1, that is isenthalpic process, so H4 will be equal to H1, and that should be uh, equal to again 59.7, right? We need to find the enthalpy at point 2 because this is in the saturation region. So it will be equal to HF2 plus X, that is dryness factor, into HFG2. Okay, so the values we have 31.4 plus 0.6 into 154 kilojoule per kg, right? So we get H2 equal to, I'm here, the value I have is 123.8. So I request you to please go through these calculation, and if there is any mistake, just let me know. Then for process 2 to 3, and that is isentropic process, right? We have S2 is equal to S3, and we can use this relation as F3 plus X3 into HFG3 by T3 is equal to SF2 plus X2 HFG2 by T2. Okay, so if you substitute the values, you get 0.2232 plus X3 into 138 divided by, I'm not writing the units. Okay, so everything is in SI units, and the some units will be cancelled out at the end. Okay, 0.1251 plus 0.6 into 154.268. Okay, so now you can solve this. Okay, for X3. Okay, so if you solve this, then X3 will come out to be 0.5325. I'm not solving this. I request you to solve this by yourself and check that you are getting the same value. Okay, so now you have quality or dryness factor at 0.3. Okay, so this is also not at this saturation line. This will also be inside the line, right? So this is 0.3. So now you can calculate the properties at 0.3. For example, enthalpy at 0.3 will be equal to HF32 plus X into X3 into HFG3, right? And if you substitute the values, you will get 59.7 plus this H3 we have calculated 5325 into 138 kilojoule per kg. So please do this calculation, and you will find that H3 comes out to be 133.2 kilojoule per kg. Okay, and H4 we have already discussed that H1 to H4 to H1 is isenthalpic process, so it will be 59.7 kilogram per kg, kilojoule per kg. Okay, so now you have all these values. Now you can find the COP, coefficient of performance. Okay, theoretical value. This will be rate of heat removal, the theoretical rate of heat removal divided by rate of work input. What will be the theoretical rate of heat removal? This will be H2 minus H1 divided by H3 minus H2, right? So H2 minus H1, this is rate of heat removal, and H3 minus H2, this is rate of power input, right? Okay, you have all these values, and if you substitute, then you will get 123.8 minus 59.7 divided by 133.2 minus 123.8. So COP, theoretical value of COP, you will get 6.82. So please check this calculation. In the question, it was given that the relative efficiency is 50%. Okay, so the actual efficiency, sorry, the actual COP. So the actual COP will be relative efficiency multiplied by theoretical value of COP. Okay, so relative efficiency was 50%. Okay, so 0.5 multiplied by theoretical value of COP is 6.82. So if you calculate this value, then you will get actual value of COP, and the actual value of COP, it will come out to be 3.41. Okay, so from this value you can find the actual rate of heat removal. Okay, will be actual COP into power input. Actual COP is 3.41 and the power input is how much? M, power input H3 minus H2. Okay, so this M is basically flow rate of refrigerant. Okay, and actual rate of heat removal will be what? This will be equal to rate of ice formation into latent heat of ice. Latent heat of freezing. Latent heat of freezing of ice. Okay, so from here you can calculate this rate of formation of ice. So actual COP is 3.14 divided by actual rate of heat removal will be M ice multiplied by latent heat of this ice, that is 418.74 kilojoule per minute. Okay, so this M ice you will get in terms of kilogram per minute. Okay, divided by 6 is the mass flow rate of refrigerant into H3 minus H2. So 133.2 minus 123.8 kilojoule per minute. Okay. If you solve this, you will get rate of ice formation as, please calculate this value. I am writing the final answer, 0.459 kilogram per minute. Okay. So in 24 hours, how many minutes? 24 into 60 minutes. So amount of ice formed in 24 hours will be equal to 0.459 into 24 into 60 kilogram. Okay. And if you just convert this value in ton, then you should get amount of ice to be 0.661 ton. Okay. So this much ice will be formed in 24 hours. Sorry. By this refrigeration system. Okay. So I hope this was clear. And now we can move to the next question. Question number 15. Again, Freon 12, Freon 12. Refrigerator produces a cooling effect of 20 kg 20 kilojoule per second, operates on a simple cycle with the pressure limits of 1.509 bar and 9.607 bar. The vapor leaves the evaporator dry saturated and there is no undercooling. Okay. Determine the power required by the machine. If the compressor operates at 300 rpm, has a clearance volume of 3% of stroke volume, we have to find the piston displacement of the compressor. For the compressor, we can assume the expansion following the law of PV to the power 1.13 is equal to constant. You can solve this question if you know these definitions. What is the clearance volume of the compressor? Okay, but I think it will be better if you solve this question after you have studied these compressors. Okay, and also we are running, we have, you know, our time is over, I think. So better if you can note down this question and try to solve by yourself when you have studied the compressors. Okay, so you can take the screenshot of this question or you can note it down. The properties are also given in this table, and we can discuss this later when we have studied the compressors. Okay. Okay, so this was last question. So we have discussed refrigerators, the how do we name the refrigerants, what are the absorption system. Basically, we have discussed ammonia absorption system, lithium bromide absorption system. Okay. We discussed one important concept, that expansion process in throttle valve is almost isenthalpic. Okay. And we discussed that in absorption system, we replace the compressor by some, special arrangement, and the purpose of that special arrangement is to compress the gas using the low grade energy, that is heat. Okay. Then we solved some numerical questions. And this last question that we will solve after we have studied the compressors. Okay. Please note down this question. Okay. So we will stop here. Thank you.